Welcome to Electrical Engineering with Excel. This is a series of videos to help you make Excel workbooks for various electrical engineering problems and circuit calculators. In this video, we will explore the use of Excel with Laplace transforms and working in the S domain. The Laplace transform is one of the most fundamental and useful techniques for circuit analysis. AC circuit analysis can be conducted in the time domain with differential equations, which can be difficult to work with. The Laplace transform converts the differential equation to the complex frequency domain, which can be solved with simple algebraic expressions. While the Laplace transform is named after its inventor, Pierre Simon Laplace, Oliver Heaviside originated much of the technique with electrical circuit analysis. When criticized for his lack of mathematical rigor, he responded with the words to the effect, "One need not to understand the process of digestion in order to eat." MATLAB by MathWorks is perhaps the tool of choice for Laplace transforms, but not everyone has a license for it. We can use Excel's imaginary math functions to do circuit analysis in the complex frequency domain. You're probably familiar with this technique, so feel free to skip ahead, but I thought a quick review would perhaps be helpful. The rate of change, d over dt, in a differential equation can be replaced with the Laplace complex variable s. The integral can be replaced with 1 over s, where s is sigma plus j omega. Sigma is the real part, and j is the imaginary operator, or square root of -1. Omega is the angular frequency in radians per second. For linear time invariant systems, sigma is not included, and s will just be j omega. The angular frequency omega is 2 pi times the ordinary frequency in hertz. Let's take the differential equation for a capacitor. The current as a function of time is the capacitance times the rate of change of its voltage with respect to time. The d over dt can be replaced with the Laplace complex variable s. The current and voltage are transformed by changing with respect to s. Solving for the voltage, we get 1 over s, which can be transformed back to the time domain as an integral. Now back to our expression for current in the complex frequency domain. If we rearrange to solve for V over I, we get the reactance of the capacitor, Xc, equals 1 over Sc. The differential equation for the voltage across an inductor is L times the rate of change in current. Using the Laplace transform, the d over dt is replaced with s. It's conventional to have the s in front of the equation. Rearranging to solve for reactance Xl equals Sl. We can use these simple expressions while doing circuit analysis in the complex frequency domain. Let's start as simple as it can get and create a transfer function for a single-pole low-pass RC filter. The equation for the output voltage over input voltage is simply a voltage divider between the resistor and the capacitor. Then simplify. We can replace RC as the time constant tau. The cutoff frequency omega naught is 1 over tau, and we can replace tau here. Then replace s with j omega. We need to convert this complex number from its current rectangular form to polar form. In polar form, the magnitude is the hypotenuse of the two rectangular form vectors. Here's the magnitude plot. In this case, the cutoff frequency is 1 kHz. A conventional Bode plot is an asymptotic approximation, but with Excel, we can calculate the exact magnitude response. The tangent of the phase angle is the ratio of the two rectangular components. Here's the phase plot. The Bode asymptotic approximation for phase has a more significant error. Turns out, we do not need to develop magnitude and phase equations for our transfer functions in Excel. We can use the imaginary absolute value and imaginary argument functions for magnitude and phase. Note these charts are log frequency charts, so to create these plots, we will need to generate logarithmically spaced frequency points. This is very easy to do. I like to make a linear series called decade and have it span 2 decades below and 2 decades above the cutoff frequency, since the area of cutoff frequency is usually of interest. Therefore, changing the desired cutoff frequency will automatically change the span of the frequency points. To generate the frequency point, simply use 10 raised to the power of the decade number. For example, a decade of -2 is 0.01 times the cutoff frequency, and a decade of +2 is 100 times the cutoff frequency. Let's say we want 50 points per decade. We can do a data fill with a step size of 0.02. Here's an example of 10 raised to the decade value multiplied by a cutoff frequency of 1000 Hertz. Continuing on to the +2 decade gives us 100 kilohertz. Let's go plug this into Excel. Okay, let's make our frequency points. Here's a column I'll call decade, and we'll start with -2, then do a data fill in series and columns with a step value of 0.02 and a stop value of 2. Then let's make this a table using Control-T. It identifies the header, and just click OK. We do not need the filter button, so we'll turn that off. Then we will create the frequency points now. Use the cutoff frequency, cell B3, and multiply that by 10 raised to the power of the decade, which starts off with 10 Hertz. And if we go down, we'll see it end at 100 kilohertz. Now it's time to create the complex frequency variable S for each frequency point. Excel has a complex function to do such a thing. It has 3 arguments: the real number, the imaginary number, and a suffix. The real is 0, and the imaginary number is omega or 2 pi f. The suffix can only be lowercase I or j. Of course, for electrical engineering, we use j as not to get confused with I for current. Here is an example in Excel. Note when using a formatted table, the frequency variable is f, is like the column header, and the @ sign means relative to that row. Relative cell names in a table assume their header name. Okay, now we'll make the complex operator S. We use the complex function. The real number is 0, and the imaginary number is the 2 pi times the frequency. And then we'll add the optional suffix as j. Okay, let's do the resistor formula now. We can see the equation to the left. 1 over 2 pi times the cutoff frequency times the capacitor. And while we're at it, let's do the E-series to return the closest standard value. And that gives us 15.8K. Now let's move forward with making the transfer function using the Excel imaginary functions. For general math use in Excel, we use the operators plus for addition, hyphen for subtraction, asterisk for multiplication, / for division, and the caret for power. Once we make a complex number in Excel, these operations must be handled using the imaginary functions. IM_sum sums the complex arguments, as many as you like. IM_sub subtracts the second complex argument from the first. IM_product multiplies the complex arguments. IM_div does division of complex numbers, with the first argument as the numerator and the second as the denominator. IM_power raises the first complex argument to the power of the second argument. IMABS returns the absolute value or magnitude of a complex number. IMArgument returns the phase of a complex number. Now let's make the transfer function, which is conventionally in the notation of h of s. Here's the transfer function we created for the low-pass RC filter. This is what will go in the formula bar. The product of s, r, and c are here using the im product function. Notice the @s designates the s-complex variable relative to that specific row in the table. _r and _c are the cell names for the resistor and capacitor. Then the imSum function adds the 1. Then the imDiv function divides the numerator by the denominator. As these expressions get more complex, it's helpful to wrap the text in places that make it clearer to read. This can be accomplished by enlarging the height of the formula bar and pressing Alt-Enter. Let's go do this in Excel. Now we'll put in our transfer function. I'm going to start off with centering these column headers. That way when we add the h of s, it will be centered too. Okay, and then in the formula bar, I'll just paste in the formula we have for that. And then expanding the formula bar, we can go up here and hit Alt-Enter to put a return in these lines to make it more readable. Now we'll do the magnitude column in decibels. That's going to equal 20 times the log of the IMABS absolute value of h of s. Now let's insert a magnitude chart. Widen the D column here and select the frequency points with Control Space, and then click Control and select the magnitude column and hit Control Space again. Then insert a scattergram. Select the frequency axis, format it to be logarithmic. Then we'll select the magnitude axis and have its horizontal cross a large negative number to position the frequency on the bottom. We'll select the frequency axis and set its minimum to 10. And we don't need the chart title, we'll delete it. We'll add an axis title for the vertical, make it magnitude in dB. Then we'll add an axis title for the horizontal, make it frequency. And we'll select the frequency axis and add some minor grid lines. Now we'll make a phase plot. Type in phase and we'll insert a phi symbol there. And that will be the IM argument of h of s. Now we can copy the chart that we made for magnitude, click Control and drag it down to make a copy. Then we'll make the axis title phase. Inserting another phi symbol. Then we'll click Control and Space to select the phase column, and hit Control C to copy. and select the chart and hit Control V to paste it in, then delete the magnitude. Now we have our phase. Notice that it's in radians. We can go back up here and put the degrees function in to return degrees of that angle. And there we have it, from 0 to 90. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.